Okay, hello everybody. So today I'm going to be giving you the first of probably many video lectures with regards to thermodynamics 3331. Giving this lecture here at my house. So you won't see my face because I'm not putting on the camera. I'm trying to keep the file size of this thing down. I've been working on it all day today trying to get this lecture right. So just some announcements about the class. So first of all, it looks like we are going to be having the class be on online format for the remainder of the semester. So that's, I know, difficult. I was really enjoying the format where we were all together and working in the Brunix Hall, and that worked out really well. But unfortunately, we're in a different situation now. And I'm giving you this lecture from my house. So essentially, you'll be hearing from me every Monday, Wednesday, Friday. I'll be posting this recording on Canvas along with the survey. So just some announcements. So as I had mentioned before, if I just kind of go back to my email that I had sent out before, so this announcement said that the lecture is going to be pre-recorded. That's the first one. And I'll post this one on the video lectures module on Canvas tomorrow by 8 o'clock in the morning. I'll also post my slides, though the slides for the control volume are already posted. So the survey, so I'm going to still be having a survey poll that's going to open at 8 a.m. and close at noon Monday, Wednesday, Friday. So that survey will pertain to the lecture or to the pre-recorded lecture that I'm giving you now, and will close at noon. So 11:59 I have it set to on Canvas AM. And so I'm hoping you can do that within that period of time in the mornings on Monday, Wednesday, Friday after listening to my lecture. And hopefully if you can get any questions you have emailed to me, I'll be trying to respond to those the best I can through email. Homeworks are going to be assigned as usual, so homework will still be assigned each Monday, Wednesday, Friday at 9 a.m. and be due the following class day at 8 a.m. per the normal arrangement. So hopefully we don't have to change any of that. In terms of discussion sections, the TAs are going to be hopefully holding the discussion sections as a Zoom or Google Hangouts meeting, and they'll send you their link to do that, and discussions assignments will be handed in as Canvas as usual. The way this is going to work, and I'll send out an additional email about this today, is that they will post the problems in the morning, and then you can join the Zoom or Google Hangout if you want to, and ask them questions via typing in through chat, or you can just do the problem as a homework assignment and turn it in on Canvas by the end of the discussion section normal time. Office hours, I'm going to be holding office hours tomorrow. My office hours are now extended from 1 to 3, and those will be every Wednesday, and so I'm going to be doing that hopefully via Google Hangouts Meet, which works really well for me. I'll essentially just leave it on and people can join and ask me questions as they want. If there are any particular questions that come up that I feel like need to be addressed overall, I will do that. In terms of the exam, it says this was back when we thought maybe we'd be back in the classroom. It appears that that's not going to happen, so I will keep you posted on what happens with the exam. And hopefully we can find a time to take it. So that's all there is for announcements right now. So so just bear with me here. I'm recording this as my house, as I said. It's quite likely that you'll hear some noises in the background. My kids, my dog, my wife, noises outside, cars going by. So hopefully there's not too much of a disruption, but I'm just going to soldier on here and do the best I can and get through this material. So the way I'm going to work this is that I'm going to have the slides up like this, and then I will also have a tablet here where I can do the examples as we've been doing before. So this should work out pretty well. So essentially I have this tablet here where I can write the example problems, which you'll see. Okay, so that's the format that's going to happen. It'd be cool to get my picture on here as well, but I don't know if that's going to happen. That might come in later. Maybe I'll just get a little screen of myself talking up here or something like that. I'm still working on the technology. As I said, I've been working on this most of the day, and the file sizes are still quite large. So I'm going to try to keep this lecture small, short, probably to about a half an hour, and we can see how it goes in terms of the overall uploading and all that stuff. Okay, so here's what we remembered from before. Okay, so remember we were doing control volumes, and as you remember that we were talking about the first law, the mass conservation, and the first law for control volume, right? So for a control volume, as you may recall some time ago, a control volume essentially is, as we've drawn here, is a system, thermodynamic system, where we have a boundary around the outside where flow goes in and flow comes out, and we can define both the mass and heat from this system using Q and W, as well as defining the inlet stream energy and the outlet stream energy. So if you remember, we do that. We developed this really big equation here for a non-steady system. So dEc v dt equals Q dot minus W dot plus the mass flow in times the internal energy and all this stuff. Remember that? Hopefully you remember that. So then what we did was we developed the work, so the flow, what we called flow work at the inlet and the outlet, and use this convenience factor called the enthalpy. And so with that convenience factor, we were able to essentially reduce the first law equation, the unsteady control volume version of the first law equation, into something pretty manageable, and we got this equation here. So accounting for both the kinetic energy terms and the potential energy terms, as you see here. Okay, so now if we look at the control volume energy rate balance, so what we have for a steady state system, and that is a system in which the control volume energy doesn't change with time. So what we call steady state are most of the things we deal with in thermodynamics. Okay, so most of the things that we do in this class are going to be steady state control volume problems where dEc v dt equals 0. And in this case, we have this following equation that we've developed and did a couple example problems for. Okay, and then if we go to one inlet and then one exit, we can get rid of the summations and go from there, and we can reduce this thing to another form here that you see. Okay, so this is where we left off before the spring break, before this whole thing happened and before I had to kind of start teaching this thing remotely. So hopefully we can do this and really get to the end of this class in good shape. Okay, so remember that we did this one where we had air in a pipe. This was a really simple example. The solutions to this one are posted on Canvas, and hopefully you've looked at these and done some homework with regards to these. Also, we did this tube one here. So what the other, this was with two-phase flow, and you did some homework problems that have to do with this. Oh, also, just a reminder, I will be posting homeworks just the same way I did before. So your homeworks are going to be due every Monday, Wednesday, Friday, just the same as they were before. Handed in the same way, graded the same way. So at least that part doesn't change. So that's good. Okay, so now let's move on. So now we're talking about different kinds of systems, different kind of steady state systems that we can analyze using the control volume method. Okay, so here we have one of these types of systems, and I've mentioned this already before, and I'm going to go through it again, okay, because you probably have forgotten or you weren't here on the Friday before the spring break. So what we're talking about here is what's called a nozzle, and a nozzle is something that has a bigger area that goes down to a smaller area, or a diffuser, which happens the opposite way. So a nozzle is a flow passage of varying cross-sectional area in which the velocity of the gas or liquid increases in the direction of flow, and the diffuser is the opposite, so where the velocity of a gas or liquid decreases in the direction of flow. So V2 is less than V1, P2 is greater than P1. Okay, so the nozzle is a pretty simple example. If we look at the nozzle and how to model it, we can see here that if we take the full first law equation, and we assume generally for a nozzle that this is the case, here where we have the first law energy, or the heat transfer is generally 0. So we assume that nozzles are generally adiabatic, unless I tell you otherwise. We also assume that the work is 0 because there's no, as I said in class, there's no shaft or no propellers or anything like that. And the change in gravitational energy, or the potential energy, is generally 0. So we don't really worry about this. So let's not get hung up on it. I mean, of course, you're not really going to have a case where the gravity difference or the elevation difference between the inlet and outlet of a nozzle or diffuser is significant. So we're going to cancel that one out. But velocities we got to keep. Okay, So if we change the potential energy from inlet of the outlet to negative, we assume that this drops out, the Z1 minus Z2 drops out, and the heat transfer of the surroundings is negligible, and the QCV drops out. And you end up with the following equation. So 0, which means it's steady state, the dECV dt equals 0, equals h1 minus h2 plus the change in the square velocities over 2, to taking into account the kinetic energy effect. Okay, so if you want to do an example, we can do a simple example of this kind of problem here. And so let's do this example together. So I noticed that one thing that everybody liked with regards to the format of my lectures was that I did lots of examples. And so now I'm going to continue that in the online format. And the way I'm going to do that, as I said before, is I'm going to do this all via a tablet. So I have a tablet here in front of me that has all this fancy stuff, and I'm still trying to figure out how to use it because I just bought it. But essentially, what I got here is this example problem. So I'll be posting this one as a PDF online, okay, on the Canvas. So let's go through this example. So air with a mass flow rate of 2.3 kilograms per second enters a horizontal nozzle operating at steady state at 450 K, 350 kPa, and a velocity of 3 meters per second. So we have air, right? So we assume that this is going to be an ideal gas. At the exit, the temperature is 300 K and the velocity is 460 meters per second. Using the ideal gas model for air with Cp equals 1.011 kilojoules per kilogram K. Remember, we were going to use Cp dt equals delta H, and we can do that here if we say there's a constant Cp. So with this, we're going to try to figure out what's the area at the inlet in meters squared, and the heat transfer between the nozzle and its surroundings in kilowatt. Okay, so these are the things we have to find. So as we usually do with these kinds of things, we have to do the, so I'm going to put this here like this, so hopefully you can see it. And then what we're going to do is I'm going to use this pen here, make sure I got the right size, okay. And then so what we always do is in these problems is we have to write down the known. So I'll try to keep my handwriting really neat here so that it doesn't get messed up, because airflow through a nozzle, okay. Okay, this is working pretty well. All right, I might actually change the size of this a little, make it a little smaller, okay. Okay, that's what we know. What we have to find in this case, oh, that's better. So we have to find is the A, so A1, and B, the thing we have to find is the heat transfer between the nozzle and the surroundings. Oh, so remember how I said that normally a nozzle is adiabatic? In this case, it's not. So we need the Q dot from the nozzle, from the control volume. So that's what we're gonna find here in this thing. Okay, so now that's the find. So now we have to draw a diagram. So let's make a diagram. So a diagram of our system looks like this. So we're going to have a nozzle. So here, let's go back. So air with a mass flow rate 2.8 enter a horizontal nozzle. So the nozzle actually means that the area is bigger and then it goes smaller, right? So the way it's going to work is like this. So we have a nozzle that looks like this, right? So then the area is smaller. It's not concentric, but that's okay. I'm still learning how to write with this thing. So we have some flow rate coming out here. We have some flow rate going in here. So here we have T2 equals 300. So we have that. We have V2 is equal to 460 meters per second. Okay, so that's pretty high velocity. All right, so we're not adiabatic. We have to define our thermodynamic system, of course. So we're going to make a dotted line around this thing. All right, so we have no work, but we definitely have a Q dot term that's coming out of this thing. So we'll show this as actually we always show Q dot as a Q dot going in. So let me just get rid of this arrow here, and then I'll just put the arrow in like that. Okay, so you just assume Q dot is going in, and then we'll find it to be a negative in the problem. So this is 0.2, this is 0.1, and so we were given a bunch of stuff. So T1 is equal to 450K. We're given P1 is equal to 350 kPa. We're given V1 equals 3 meters per second. And we're going to say CP is going to be constant at 1.011 kilojoules per kilogram K. All right, and let's see what else. We have mass flow 1 is equal to 2.3 kilograms per second. Okay, so it's ideal gas, so let's make some assumptions here. So some assumptions that we need to make for our problem are that we have we have ideal gas with constant specific heat. B, we have let's assume that there's no work of the control volume equals 0. There's no shaft work. It's not adiabatic, and so essentially delta PE is equal to 0. So there's no potential energy change. And then of course we have to assume that's a steady state problem. Okay, so it's steady state. Fine. All right, now let's go on with the analysis. So in the analysis, we're going to assume here that let's see. Sorry. So m dot 1 equals m dot 2 equals m dot, because there's only one inlet and one outlet. So that's the first thing we have to assume here. And that m dot is equal to A1 V1 over the specific volume at 1. So that's something we have to also assume here. And we can figure this out because we know what the V1 essentially from the ideal gas law is R T1 over P1. So by the ideal gas law. Okay, so then we can substitute this in and get what we need for A1. So A1 is one of the things we needed to find, right? So A1 is equal to m dot RT1 over, let's see, the velocity, oops, why I keep doing this, over velocity 1 times P1. This is velocity. Okay, so this is going to be pretty straightforward to do. So if we want to just solve this thing, so we know what the mass flow rate is, 2.3 kilograms per second. We know that this is 8.314 divided by 28.97 for air times 450K all over, so this is 3 meters per second and 350 kPa. So the kPa in 8.314, that works out well, so we don't have to do any unit conversions, and then we end up getting something that looks like this, 0.2829 meters squared. Okay, so that's the next, that's the first thing we need to find, rather. So that's a pretty simple thing. We don't need to use the first law for that. Now for the second part of the problem, we need to use the first law, right? So let's do that on the next page. So now say continued here. Example 1 continued. Okay, so the next part is that, so assume that B, so we need to find the Q, Q dot. So here we assume that this delta H that we have is equal to CP delta T, because this is a constant. If I said that we don't have constant specific heats, then you wouldn't be able to do this, okay? But since we said this is a constant, that's cool, okay? So now let's go with here. So we have one inlet and one outlet, and now we can simplify this thing. So 0 is equal to Q minus W. So we're going to just put all the terms in here just so we can cross them out for fun. M dot, let's see, H1 minus H2 plus 1/2, let's just zoom up on this, V1 squared over V2 minus V2 squared. And we're just going to neglect the gravitational term. So the gravity term is not here. No delta PE, because I ran out of space. I ran out of space. Okay, so this simplifies now if we assume this is 0, because there's no shaft work, right? So as we said before, this simplifies to Q dot is equal to M dot CP T1 minus T2. Oh, I'm sorry, T2 minus T1, because 2 minus T1, because we just switched the signs. Remember, see how I put the Q on the other side of the equation, so the T2 and the T1 go to the opposite sign. So now we have the velocity term 1/2 V2 squared over 2 minus, oops, shoot. We gotta get rid of V2, let's see, V2 minus V1 squared. There we go. That works pretty well. Okay, so now, let's see, do I have another bracket? Yes. Okay, so let's see, do we have everything we need? So I'm going to go back here to my problem here, and it looks like, yeah, it looks like we've got most everything we need here. We've got the inlet temperature, velocity. I think we have everything we need. So let's, here I go to the next page and essentially finish this off. So just substituting. Substituting, we have, so Q dot equals 2.3 kilograms per second times something big here. So we're going to have 1.011 for CP times 300 minus 450, because remember the temperature went down, plus we're going to have here 460 squared minus 3 squared over 2. And let's see, since we have velocities here, we're going to have to do correction, right? So this is meters per second, so we're going to need to do kilojoules. So 1 over 1,000 on the kilojoules. So let's just put this here, kilojoules per Newton meter. Okay, because this is meter squared per second squared, and we want to get that right. So essentially that's how this comes out. So make sure if you have the velocity here, so if you have this velocity here, you can always, I don't know if I can use a pointer. I haven't figured out pointer yet. So if you have the velocity, so essentially I point it with here. So if you have the velocity here, you need to make sure you divide by 1,000. So I'm going to put this in parentheses because this is in meters per second, meter squared per second squared, which converts, you need to convert into kilojoules per kilogram. Okay, so that you need to use the factor of 1,000. So then I think we can close the big bracket here, and then essentially here we have Q dot is equal to negative 105.5 kilowatts, and so this is the answer. So this is actually, we're going to say heat from the control volume to surroundings. Okay, so that's how we do this problem. So essentially, you know, we can see that the heat is lost from this system because we have a minus sign in the Q dot. Okay, so all right, so that's the nozzle problem. So it's pretty simple, right? I mean, I don't think this is really difficult to figure this out. We just have to know how to apply the control volume form of the energy equation. Okay, so let's move on. So the next thing we need to figure out here is on turbines. So turbines are a special kind of device. Turbines compressor are a special device which power is developed as a result of gas or liquid passing through some blades. Okay, here we have a stage blades. We have small blades to large blades. In this case, we have an expander. We're expanding, we're making power. In this case, we have turbine modeling where we have the change in kinetic energy being negligible. So what we're going to do is develop the first law for a turbine. And this is going to be the same for a compressor too. I remember doing this in class, so I'm going to do this again because some people weren't there and we have this lecture. Now, if you notice that I'm at home, there's somebody grinding wood chips outside my window. So that's just the way these lectures are going to go. Okay? I have no control of that. So hopefully you can hear me just fine. So my microphone is right here. Okay. So here the first law, we can see here that that again we have a steady state problem. So 0 equals Q dot minus W dot. Again, we can assume this generally goes to 0, the heat term, because we're generally adiabatic, except when I tell you that it's not adiabatic. So make sure you're paying attention to the problem. If there's no heat given, you assume that it's probably adiabatic, okay? Or you say that it's insulated, and there's some code words for that. There's obviously work, so that we have work coming from the control volume, and then we have these terms here for the change in enthalpy. We generally we can change out the kinetic energy terms, but we don't always do that, right? So it just depends on the case. But generally the potential energy terms go away, so we don't worry about that. So if this is an adiabatic turbine with heat transfer to the surroundings being negligible, we essentially get this very simple equation that W of the control volume, or for a turbine, equals m dot H1 minus H2. Okay, so that's the exact same as I said for a compressor, so we don't worry about that. Okay, so compressors or pumps is the same kind of deal in which devices work done on the substance. And as I said in lecture, there's a bunch, we can do these roots blowers, we can do a bunch of other stuff, so these are different kinds of compressors that you might see. However, from a thermodynamic standpoint, from what we're going to be doing here, they're going to be exactly the same, okay? So the change in kinetic energy, so in this case, the pump compressor runs up into the same equation, right? Ends up in the same equation, W dot CV equals M dot H1 minus H2. Okay, so let's do another example. Let's just do one more example here, and we can see how this turns out for doing a compressor. And this will be the final thing that I'll do today, is this example for the turbine. And so I'll be giving you some homework that has to do with turbines and compressors, so that you can practice these. Turbines and compressors are actually and pumps are the most common thing that you're going to find in thermodynamics. So it's probably good for us to do these examples and get these done. Okay, so here we go. Here's what we're going to do. We're going to do this problem, and I'll put it up on my tablet again. So here we go. Steam, is this the same one? Yeah, this is the same one, right? Yep, okay. Good. Steam enters a well-insulated turbine operating at steady state, 4 megapascals, and with specific enthalpy given. Actually, I seem to remember doing this problem in class. But I'm going to do it here. I may not have posted this one online, but I seem to remember doing this one in class, so I'm going to do this one again. So we have a very simple problem here where we're given the enthalpies. We don't have to look them up in the table, and we can kind of move on. So let's see here. So let's do this one here. So what we have known. So we have known that that we have a steady state turbine. Yeah, can keep this one there. Okay. And then essentially we have that we need to find is the power developed by turbine. So that's W dot. Okay, finding W dot. Okay, so now we're going to make our assumptions. Oh, actually, we can make our assumptions first. Doesn't matter which way you do this. So if we make our assumptions first, we're going to assume that we have steam, steady state, And we have B, well insulated. So well insulated generally means that we have a adiabatic turbine. Okay, so adiabatic turbine, properties given. So let's just draw it. So generally a turbine you draw like this, and then you have condition 1, condition 2. Okay, so then you have some power coming out, and then you got to make your control volume boundary. It's always good to do, and sometimes it's always good to label it control volume. Okay, so that's your control volume there. So coming in, so you have, let's see, P1 equals 4 megapascals. H1, you don't have to look in the steam tables because it's given to us, 15.4 kilojoules per kilogram. And V1 equals 10 meters per second. We have here, let's see, we have M dot given to us is 11.95 kilograms per second. Okay, kilograms per second. And then we also have that, yeah, we have the condition of 2. So we have P2 equals 0.07 megapascals. And we have H2 is equal to 2431.7 kilojoules per kilogram. Okay, and what's else? We have V2 equals 90 meters per second. Okay, so there's our diagram and our assumptions. So this means that Q dot equals 0. Okay, so now let's just reduce the equation. So analysis. Analysis looks like this. Essentially, we have 0 equals Q dot minus W dot. Here, I put this here. Minus W dot plus mass flow rate H1 minus H2 plus V1 squared minus V2 squared over 2, and neglecting potential energy. No delta PE, because again, I ran out of room. Okay, so all right, so we have that. Now we're just gonna get our final rearrangement here of the equation, and equals M dot H1 minus H2 plus V1 squared minus V2 squared over 2. Okay, so I think we're given everything, right? So if you look at this whole thing, the pressure is not needed, right? So these guys actually weren't needed at all, these pressures here. But you can see we drop pressure through the turbine. I guess if you were to look that up in the steam tables, you would need that pressure. But in this case, you don't need them, so we're going to just go without it. So we're just going to do the final solution here. Solution. We're going to get that we have work is equal to 11.95 times 3015.4. This is the mass flow, right? M dot minus 243. Oops. Here, let's erase some of these guys. This is starting to look messy. Okay, so let's do this again. So we have 11.95 3015.4 minus 2431.7, and we have to then, of course, do the correction here for velocity. So this is the kinetic energy term divided by 2, and then we're going to have a 1 over 1,000 again. Remember that, like we did just before. And then essentially what we've got here then is, let's see, this is the very same kind of equation that we set up for the nozzle. It's very, very similar, right? So then we're going to end up here, if we just kind of finish the deal, we have 6927 kilowatts. So this is positive. So it's work out of turbine. Okay, so that's how we do it. That's how we do that thing. All right. So now let's see. we're at 35 minutes here. So I'm going to keep on going a little bit and see what we can do with anything else that we have to cover. So okay, so as I said, I may have done that one before. We can also do this example here, compressor, though I may save that to the next lecture. Oh, maybe I'll just do it now. I mean, we can just do it now, right? So let's just do one more. Let's just do one more example here, and I think this is also a pretty straightforward one to do. So I'll post this one as well. So let's just do this example, and then I can quit after this one. How's that? All right. So let's see now. So let's see if I can move to the next example problem here. So this one is just a compressor. So this is like the opposite of the turbine, right? So it's just the opposite of the turbine. So we can see that we have air modeled as an ideal gas, compressed at steady state from 1 bar 300K to 5 bar 500K with power input. Right, so we have power input. Heat transfer across at a rate of 20 kilowatts from the air to the cooling water. Oh, so we actually have not an adiabatic compressor here. Neglecting the kinetic and potential energy effects determine the mass flow rate of the air. All right, so let's do this let's do this quickly here. I'm going to go even smaller here and get in more material here on the page. So what we have known is that we have air through a compressor. Okay, so that's known. We have data provided in the inlet and the outlet, and what we have to find here is we have to find the m dot. Okay, pretty straightforward. So let's do our assumptions. So our assumptions here are A, that we have ideal gas. Are we going to assume constant specific heats? I don't think so. I don't think we're given constant specific heats. We're going to have to look these up. We might have to look things up. We have to use the tables because it doesn't say constant specific heat. So if it doesn't say constant specific heat, we're not going to assume it. Okay. B, we're going to assume that's steady state, and we're going to neglect, so no delta PE and no delta KE. So essentially, we're just going to write this analysis up pretty easily. Okay, and we may not have to write out the entire first law equation because we have a good idea. So let's make our diagram. So compressor is kind of drawn the opposite of a turbine. So it looks kind of like this, and then you have stuff coming in and getting compressed, going to the small side of the turbine. You have some work that's coming off of this thing, and in this case we have some heat. So I'm going to draw this as Q dot going in, because that's the way we always draw heat. Okay, and so now let's see, we have P1 equals 1 bar, and we have T1 equals, oops, I kind of messed this up here. Let's just get rid of this. Okay. T1 equals 300K. And we have P2 equals 5 bar, and T2 equals 500K. And then we have QCV, or Q from the control volume, is 20 kilowatts. Okay, I think that's all we're given, right? Yeah, that looks like it. Okay, oh, and 150 kilowatts. We have W dot equals 150 kilowatts. Now, this is work in, right? So this is negative, and then I believe this is transferred from the air to the cooling water. So this means it's into the control volume. So this actually is negative as well. So let's just see how this works out. Let's see. Let's clean this up a little bit here. Equals minus. No, I think we're good here. Okay, so now let's do analysis. So the analysis is the following. Essentially, we're going to say 0 equals Q dot minus W dot plus M dot H1 minus H2, and we're going to neglect delta KE, and delta PE. And we're not even going to write them in the equation, okay? Because we're advanced now, and we're not going to even do it. So then we're essentially going to get to the equation for m dot. So solving for m dot, we end up getting m dot equals q dot minus w dot over h2 minus h1. And that then we have all we need, but the problem is that here we have to look this up in the table. So h2 and h1. So h1 and h2 we can look up in tables. I believe it's in table A22. You can look those up because I'm running low on time here, and I want to keep this lecture somewhat short. So we can look those up in table A22 in the back of the textbook. You may or may not need to interpolate, probably not, but I think we can just assume that you guys know how to do that. So if H1 is, I have it written down here as 300 about kilojoules per kilogram, and H2 is equal to 503.02 kilojoules per kilogram. I mean, really, forget about the 0.02. This is ridiculous. Kilojoules per kilogram. I mean, we don't need to do 0.02. Then essentially what we can do is we can solve for it. So m dot then is equal to negative 20, because remember we said that it's negative 20 is minus a negative 150 divided by 503 minus 300, right? And for that, we end up getting a solution of 0.64 kilograms per second. Okay, so end up using the first law here, first law as your analysis tool. Okay, that should give you a pretty good handle on using the first law for control volumes. And let me go back to my slides. So this means next time we're going to cover heat exchangers in our lecture. So heat exchange would be the next thing we talk about. Your homework is going to have to do for this time, for due then on Friday, will have to do with turbines and compressors, and also your example and your discussion will probably also have to do with those things. I'm going to move on to heat exchangers next time, and then after that we're going to probably be finishing up with control volumes and moving on to something else and to a new subject. So with that, I'm going to end my first video lecture, and I hope that you guys were all able to see it. Please send me emails and feedback if you can, to let me know how this is going and whether you have any additional recommendations for how I post these. Okay, stay healthy, and we'll talk to you next time.